All right, let's start today's class. Okay, so we are still working on the assembly crash course module. Before we begin, are there any questions about the class as a whole at a higher level? Nope. And we'll see if any show up in the Twitch chat, but I will continue on in the meantime. Are there any conceptual questions about this module that don't necessarily relate specifically to levels or anything about this module itself? Yeah, question?
So the whole idea is you'll run the challenge,
Mhm.
get a certain piece of code to do something, write that's is that the overall?
Yeah, so basically you're given some description of what your program needs to accomplish, and then if you match that description, you get the flag.
Well, in assembly.
Yeah, you write everything in assembly. Yep, yeah, you're providing raw assembly at the challenge. I guess, yeah, just to be sure, because I know that there's some people that haven't quite had a chance yet to start, we'll just very quickly look at level 1 to show what that looks like, just so it makes more sense. For those starting late, highly recommend, hopefully everyone started, but I know that's not the case necessarily for everyone. Let's see here. Okay, so the way that we've been demonstrating it, and you can always look back for anyone that is just starting now at previous Q&A videos, but the way that we have been running these challenges, and actually let me just manually run it first. If we look at level 1 real quick, we will see, basically says, depending on the level, it will give you a whole bunch of information. This module is very information heavy in terms of what the challenges tell you. But in the case of this first level, it's saying, hey, just set the register RDI to hex 1337. Again, if that doesn't make sense, watch the videos. The videos will explain all of the concepts explored in this module. So it's just looking for raw bytes of assembly. So the way that we have been doing that, if you look back at the previous videos, you'll see something like this. We have been doing, process this. We have been doing a template that looks something like this, where we are using pwn.tools, which is a library within Python for interacting with processes and then also writing assembly and doing all sorts of other things. We create the process, which is the challenge, and then we just write our assembly that has been assembled straight at the challenge. So for example, we give it the int3 instruction, which is kind of a debugging. Hold on, let's go back to level 1, which is a debugging instruction. We will see after some time that it sends that assembly straight at it. So we can see it executes your code, disassembles our code for us. It says, hey, we're running the int3 instruction. And then in the case of the int3 instruction, it gives us a whole bunch of debugging information. In the case of this first challenge, it just says, hey, set RDI to 0x1337. The way that we set a register to some constant value is using the move instruction. So we do move RDI 0x1337. And matching the description of what it's asking for, it will give us the flag. Okay, yep. So that's kind of at a high level what this all looks like. Are there any more questions about the module at a conceptual level, or any more high level questions? Oh yeah, there's a question here. A conditional jump statement? Yes. Okay, so the way that you do a conditional jump statement, and I forget which level looks at this, but we can just use level 1 to kind of see what this looks like. Is level 10? Either way, we'll just show it off real quick in this level. I think we might have a previous Q&A video that talks about level 10, but we'll just quickly show it here. The basic idea, so let's, for example, say that RDI is set to 1337, and we want to conditionally jump based on whether or not RDI is 0x1337. So let's, for example, say compare RDI to 1337. So what this instruction is doing is it's saying it's doing an operation between RDI and 0x1337 and setting a bunch of flags determinant on if it's greater than it, if it's equal to it, a whole bunch of different flags, which the videos talk about in control flow. This will talk about all of the different flags that are being set. But let's compare RDI with 1337, and then let's say jump equal to this label here, which we're going to set up. So we'll even call it jump here. And then we create some label, for example, jump here. And in this case, we will run move rax1. And otherwise, let's see here, it's equal. Otherwise, we'll move rbx1. Let's just show this as an example. So this here is we're initializing RDI to hex 1337. We're comparing RDI with hex 1337. And if these two values that happened in this previous compare instruction are equal, if RDI is in fact equal to 1337, we're going to jump here, which means the next instruction that we'll execute is this move RAX instruction. Otherwise, if that's not true, if they're not equal, it's just going to continue on to the next instruction, which means it's going to execute this instruction instead. And then it would fall through to this as well. So basically, if they are equal, RAX will be set to 1. If they're not equal, RBX will be set to 1, and RAX will also be set to 1. So let's look at that just as proving that is the case. So we can see that because they are equal, hold on, let's see what we were looking at. Because they are equal, we are expecting that only RAX will be 1 and RBX will not be 1, because we should have skipped this instruction since they are in fact equal. Let's see that RBX is not 1. And we can see, yeah, RBX kept its 0 value, but RAX was set to 1. Alternatively, if RDI was not 1337, let's say it's 1331, we will see that instead they're no longer equal, which means we're not going to do this conditional jump, which means we're just going to fall through to this and then fall through to this. So both should be set to 1 now. And we will see that in fact both are set to 1. Does that answer your question about conditional jumps? Perfect. Okay, any more conceptual questions about x86? Any instruction or concept within x86 that doesn't quite make sense? Okay, then we will jump into the levels. So does anyone remember what level we left off in the last one? Was it 18? 19? Okay, let's take a look at 19 then, because we didn't quite finish that one. So we should take a look at it. Oops. Okay, so let's open up, actually let's first just run the challenge. See what this challenge was telling us. I believe it has to do with jump tables. Yes, okay, so as a reminder, if we remind ourselves back at level 19, we have this concept of what is basically an indirect jump, which means we have this table of instruction addresses just sitting in memory. And rather than jumping either conditionally to some location or directly to some location, we jump indirectly, which means we're going to dereference memory, and whatever is at that location in memory, that's the address we're going to jump to. So for example, we can imagine this situation here of a jump table. So we can say that at location hex 1337 in memory, we have this jump table, which needs to be a series of addresses. So let's say we have a bunch of different things we want to do. If you can think in the world of C of a switch statement, let's say the first thing we might want to do is do thing 0. And that's going to contain the address of instructions in memory that correspond to the logic of do thing 0 at offset 8, right? Because the size of an address is 8 bytes long. So 8 further, we have another address. And then 8 bytes further, we have another address. 8 bytes further, we have another address. Which means that if we were going to jump to dereferencing one of these values, we're going to jump to one of these addresses. So let's see what that looks like. Actually, and let me try to find a way to explain this a little bit clearer. Process. So we're working within level 19. Let's make sure this works. Okay, so actually, let's open Emacs instead. Example. Okay, so let's imagine we have memory that, let's say, at hex 1000, we have 4000, for example. And then we'll actually, hold on. Before we do that, let's say first that at hex 4000 in memory, we have instructions. So let's say at hex 4000 in memory, we have the instruction move RAX1. And then let's say at 4100 in memory, we have the instruction move RBX1. At 4200 in memory, we have this instruction. And here in memory, we have this instruction. So let's say that these are instructions living in memory, right? We just have single instructions, and then we can pretend that after here, we haven't talked about the halt instruction, but the halt instruction is this privileged instruction that just halts the CPU. So let's pretend there's nothing after. Okay, so let's say in memory, we have these two instructions, etc. So basically, we're going to either set RAX to 1, RBX to 1, RCX to 1, or RDX to 1. Well, in memory at a different location, so obviously these are all executable. This is an executable region of memory because instructions are there. We're trying to execute these instructions potentially. At a different location in memory that doesn't need to be executable because we're just containing addresses, we're not containing instructions, we have the following. We have 4000 here. We have 4100 here. Oops. We have 4200 here. And we have 4300 here. So we have two different regions of memory. One region of memory is executable, and one other region of memory is data, basically. And that data is containing addresses that point to executable memory, right? This contains this address that contains these instructions. So what happens now if we're going through and executing on our CPU, and we want to conditionally execute one of these operations? Actually, let's not even explain that first. Let's make this even simpler. Let's say that we want to, for whatever reason, we want to jump to this 4000 address, right? We decide we want to execute these instructions right here. Well, one thing we could do is we could just say jump 0x4000, or more likely, because of what is available for us, we might have to do something like move RAX hex 4000 and then jump to RAX, right? So this sequence of instructions is just going to always jump to hex 4000 every single time. Well, what if instead we want to jump to 4100? We can do that, right? We can update our assembly, we can update our assembly, we can update our assembly. But instead, what we can do is we can have a layer of indirection. So what we can do is, let's see here. Let's say that we have some register RDI, and we want to conditionally jump to one of these regions based on whether or not RDI is 0, 1, 2, or 3. So initially, let's just say RDI is 0. Well, because we have this jump table in memory, we can just start doing math to figure out how we're doing that sequence of jumps. So if we do, for example, move RAX hex 4000, right? And then if we do, actually, we'll make it even simpler. We don't even need to. Let's jump here if it's, so let's say this. So if RDI equals 0, go to 4000. If RDI is 8, go to 4100. If RDI is 16, go to 4200. And if RDI is 24, go to 4300. Okay, so let's say we want to encapsulate this logic. If we wanted to encapsulate this logic using traditional instructions that we've previously explored up till this level, we would have a bunch of compares, right? We would basically say compare RDI 0, jump equal, if it's equal, jump to RDI, jump to move, we'd have something like this. We'd move RAX 4000, and we'd jump if equal to RDI, to RAX, excuse me. So right, oops, that went away. So we would do, this would encapsulate, hold on. That would encapsulate this first if statement, and then we'd need another one. So we would say now compare this with 8, and if it's 8, we want to go here. And now if it's 16, we want to go here. And if it's 24, we want to go here. So this is one way we could encode that logic, all of this. But instead what we can do is we can just throw all of this out and use this layer of indirection to make it so we have much less instructions and also much less comparisons. Because you can imagine if we are 24, we're going to have to walk through all of these instructions before we finally find the 24 and what we're interested in. What if we could just instead go straight there? So here's how we can go straight there. So if we get rid of all of this, actually, let's just get rid of the compares. Instead, what we can do, well, let's leave them for now. So we'll say this right here. This. Okay, and let's grab our jump table. So instead, we could just throw this straight in memory, all of these addresses we want to go to. And what we could do is we could move the base of our jump table into RAX. And then what we could do is we could add RAX RDI, and then we could just jump RAX. So see how we didn't do any comparisons here? No comparisons were necessary. No several checks needed to be performed. Instead, we just have this layer of indirection where at the first offset is hex 4000, right? That's the base of all of this. Wait, hold on, that's not true. Well, I guess, hold on, let's see here. In this case, this would work, right? We're not actually using this jump table. Hold on, we'll get to the jump table in a second. We could do this right here. This would also work, right? We just take RAX, set it to 4000, add RDI, and jump there. Wait, no, that's not true. We could multiply RDI by like 25 or something, or whatever value, and jump there. We could imagine doing that. But hold on, let's make this slightly more complicated. Hold on. Let's say that this is right here, and then these are just like non-symmetrical addresses, or not like following this pattern. That's all over the place, let's say instead. So we're here, we're here, we're here, right? So there's no like obvious math relationship between all of these addresses. So what we can do is store this in memory, all of these addresses. Actually, let's just type them all in. It'll be quicker. 4108, 4222, 4333. So we just have this all loaded into memory. And now what we can do, get rid of this, is we can move RAX hex 1000, add RAX RDI, because RDI contains either, let's say, 0, 8, 16, or 24. And then we can dereference RAX. So we can move RAX, comma, dereference RAX, right? Basically, right now we're going to have either 1000 sitting in RAX, 1008 sitting in RAX, 1010 sitting in RAX, or 1018 sitting in RAX, depending on if RDI is one of those values. We dereference memory, which is going to extract one of these addresses for us. And then we can just jump RAX. And now we don't need all of those comparisons. We just jump straight to where we're going by doing this memory dereference to tell us where we're going. So certain things need to be true in order for this to work. We need certain properties on RDI. So for example, we're assuming right now that RDI is going to be some multiple of 8. If RDI wasn't some multiple of 8, instead what we could do, for example, let's say RDI, instead of being RDI equals 0, 8, 16, or 24. We're just assuming that this is true. If instead RDI was going to be 0, 1, 2, or 3, right, we could just multiply by 8, right? Hopefully it's clear that before we do this add, we would just do a multiply, right? We would say like, we would just say like, we're not even going to write it in assembly. We'll just say like RDI equals RDI times 8, right? We'd multiply RDI by 8, and then we'd be able to do the exact same thing. So this is the whole idea of jump tables. The whole idea is skipping all of these comparisons by needing to walk through and figure out all these comparisons. Are we 0? Are we 8? Imagine a long chain of else ifs, else if, else if, We want to just get rid of that, throw a bunch of instruction addresses in memory, and just compute where we're going to jump to. This is the basic idea. Okay, anyways, back to this challenge. Okay, so this is telling us, here's an example table. So, and also it's telling us a number of things. So it's telling us that RDI will not be negative. It's telling us not to use a bunch of comparative instructions, just to basically make sure we don't do that else if sort of logic. Instead, we do an indirect jump. And then there's other requirements. Okay, so the number that we're switching on is going to be in RDI, and the base address of the jump table is going to be in RSI. So here is an example table. So in this case, this would be the base address. So this would be RSI, would be right here. And then we would be adding 8 and then adding 8 more and adding 8 more, adding 8 more to get all the way through all of these values to contain where we want to go to effectively. So let's see here. So we need to do this logic right here. Jump table address plus our number times 8. Like I said before, we would do that times 8 if it's going to be 0, 1, 2, or 3 instead of already being a multiple of 8. As likely you're not comparing things that are all just multiples of 8, but be a performance gain if you were. Okay, so let's see here. So for example, in this first example, we have RDI being set to 4, and then RSI is being set to here. So this is the base of our address table, and then this is our number that we're switching on. And one other thing we need to know that we did not talk about before is kind of the concept of a default case. So like, what if it's not any of those? Where do we go? Well, in this case, we would be jumping here, which looks like it's the last entry in our jump table. So we can imagine basically if it's not 0, 1, 2, or 3, that we should just like set RDI to be 4. And just default on 4 and make anything that's not one of the explicitly mentioned things become 4, so that we will just always jump to that default case. That's kind of like a quick way to solve that problem. Okay, so let's go ahead and multiply RDI by 8 so that we're ready to get ready to index in. So one way that we can do that is using the load effective address. So let's see that real quick. So what we can do is we can load effective address. Let's just set RAX to be whatever value we want it to be. Let's see here. So we want to do RSI plus RDI times 8, basically, right? This is what we want, right? This is the base of our table, and we want this times 8, and that's where we're about to jump to. So let's make sure we're doing that correctly. In 3, and see that we're correctly computing that. Okay, so we just performed that. So what we're saying is we want this plus this times 8, and that should now be inside of RAX. And we can see that is in fact now inside of RAX. We've done our first series of calculations to find our offset into the table. And now we just need to dereference memory and jump there. So, and then also we need to deal with that else case as well. So let's actually deal with that first. So let's say, let's compare RDI with what our value, our other cases. So we have 0, 1, 2, or 3. So let's see what happens if we're above 3. We want to set to 4, basically. So if we compare RDI with 3, and then if we're above 3, so JA, if we're above 3, we want to basically set RDI. Actually, if we're not above, let's say, is that actually an instruction? We're about to find out. If we're not above, we want to jump here, right? We don't need to worry about it if it's not above 3. If it is above 3, then we want to move RDI 4, right? We just want to default to 4. So if we're not above, we jump here. Otherwise, we set to 4, and then we automatically fall through here. So let's see if JNA is in fact an instruction. Hopefully it is. Jump not above. Okay, it looks like it is. Sweet. Which is also the same as jump if below or equal, right? Not above, below, or equal, same thing. Okay, so we've got that logic handled now. So we can see that in this case, RDI was 0, so RAX in the end ends up as the same because that's how we're multiplying in. Let's see if we can get any where it is above 3. This is 2. We might not be able to see a case right away. We can ignore that temporarily if that is the case. This is a case where it's 1. We're looking for 1 where it's above 3 to confirm that our logic is working. This is 3, not above 3. Nope. Possible the very first test case is not possible for it to be that. So let's ignore that for now. We'll confirm later if we're wrong. So the next thing we need to do is we've got the address of where we want to jump to of our jump table index basically loaded up into RAX. So now we need to dereference RDX. So basically we can just say move RAX, dereference RAX. So for example, we have one of these addresses currently loaded in, and we want to dereference to get to where we're trying to jump to. So in this case, now we would have this sort of value in RAX, and then we would jump to RAX. Jump RAX. And we'll put our int3 there because once we jump, we're not going to execute our int3 because we're off of where we were. We're getting a lot of data right now because we were correct in the end, that we passed the test case. Let's actually quickly, to confirm this logic right here, let's break this case. So let's, for example, instead move RDI 0. So we would not be jumping to our default case. In this case, we'd be jumping to the case where RDI is 0 so that we can get to the example of what we were talking about. Actually, in fact, we can make this even easier. We can int3 right here before we do that. So we'll see that test case example where it's above 4 or 4 or equal. Right, yeah. So for example, RDI right here is now 5, and that is the situation that we're handling up here to go to that default case. So instead of moving RDI 3, we move it to 4 because index 4 into that table contains our default address. So that's why we set that to 4. And goes through, runs all those test cases, and eventually it passes. So that is the idea of a jump table. It's a little conceptually confusing probably compared to a lot of these other concepts because you're kind of really working with pointers, and in this case you're working with code pointers. It's effectively a performance optimization so that we don't have to go through a series of compares. We can just abuse memory, add a layer of indirection, and just jump straight there. That's kind of the idea there. Little complicated for sure, but that is the basic idea of what's going on here. Okay. Perfect. So any more questions actually real quick on level 19 about these jump tables or anything surrounding these jump tables? Okay, I don't see any. Okay, you had a question about different level?
Oh, yes. Level 21.
Level 21? Out of memory error on level 21. Let's see. Yeah, I can see the chat also has lots of questions on 21. Okay, let's see what level 21 is talking about. Okay. So it looks like in this challenge, we're going to be kind of writing a real program in some sense, doing some actual operations that result in something that means something, because we're computing an average. Let's see here. So previous levels talked about for loops, both dynamically and statically known, but what happens if you want to iterate until you meet a condition? So in the world of C, this would be like a while statement or a while condition. A second loop structure exists, called the while loop to fill this demand. In the while loop, you iterate until a condition is met. So let's see here. So for example, if we want to walk down a list of numbers and just keep summing them until one of those values in our list is 0xff. So we're basically saying that 0xff is kind of a terminating thing in the same way that in C, a null byte is a terminating character for a C string. In this case, we're imagining this list of numbers where 0xff is kind of our terminator. And we want to add all of those together, and at the very end, we want to divide by the number of things we added together. Okay, so using the above knowledge, please perform the following. Count the consecutive non-zero bytes in, oh, actually, well, did I say that wrong? Is it going till 0? Well, xi is less than ff. Not clear. We'll get there, though. Count the consecutive non-zero bytes in a contiguous region of memory where RDI is the memory address of the first byte. So this is going to be the start of our list. RAX is the number of consecutive non-zero bytes. Wait. RAX. Count the consecutive non-zero bytes in a contiguous region of memory where RAX is the number of consecutive non-zero bytes. Okay, well, I'm not sure why they're telling this if we're going to go until a terminator, but we'll look at that in a second. Additionally, if RDI is 0, then set RAX to 0. So this is basically a null check. If we don't have a list, instead our list is null, we're handling the null case because we don't want to dereference 0. We don't want to dereference effectively a null pointer if we kind of think to the C world. There we set RAX to 0. Oops. Hold on. Okay. Do that. So as an example, yeah, this will make it clearer. So if we have RDI set to hex 1000, and then at hex 1000 in memory, we have 41, 42, 43, and then I guess the last one is null. I think there might be a typo then in this logic, but okay, here, here, here. So then we have 0 being our terminator instead. Then RAX equals 3 should be set. So we want to, okay. So here's what's going on with this RAX. This is our result value. It's not giving us RAX. This is where we're storing the result is into RAX. Okay, let's start working on that then. Here's an example one. At 4,000, there. Okay, so we want to basically just walk memory until we see a null byte is what we're trying to do here. So we're just going to go byte by byte in memory, and as soon as in memory we see a null byte, then we're done. And we're just trying to count how many values we explored in memory. Okay, so let's go into IPython. So hopefully it makes sense, right? If we have single bytes in memory, let's say we have 1, 42, 33, 19, 17, 0, 104, 1, 255, 104, whatever, something like this, just sitting in memory, single byte sitting in memory. In this case, we would say that the result is 1, 2, 3, 4, 5. We'd say the answer is 5 here. So even though there's values after, we don't care. We're just going until we see a null byte. So in some sense, we're taking the stir length of a value, right? Because strings are ended with a null byte, so we just would walk memory until we see a null byte. That is what stir length does, effectively. So let's implement stir length then. So we want, actually, let's quickly, just so it's a little bit conceptually easier, let's just implement that in Python and then implement that in assembly. So let's say that this is our list. We'll say list equals this. And then we're going to say while, and then we're going to say I equals 0, while list of I does not equal 0. We're going to do I plus equals 1, I plus plus basically, and then print I, right? So in this case, we walk the list 1, 2, 3, 4, 5, right? Every single time. This is the value we're looking at now. Whoops. Right, we're looking at 1, we're looking at 42, we're looking at 33, we're looking at 19, we're looking at 17. Ultimately, then we look at 0, we see it is 0, so we exit out of the loop, that's 5. That's the concept we're trying to implement within assembly. Okay, but instead of list being a Python list, what we're going to have is an address in memory that contains all of these bytes at RDI. Okay, so let's start with an int 3. And this is level 21, I believe. Okay. So we can see sitting in memory is a bunch of bytes. This is displaying it to us as 8-byte integers. In reality, we're working on 1-byte integers, 1-byte values. So we can see here, we've been walking through all of this. We still don't see a null byte. We still don't see a null byte. Let's Control F for a null byte. Is there actually not a null byte in there? It might be past the bounds of all of this. Let's run it one more time. Hopefully we get a null byte quicker. Where is our null byte? So RDI is initialized to here. Yep, still no null byte. Okay, maybe the null byte is guaranteed to not appear in this first portion of memory. Whatever, we'll work with it. Let's start implementing it. So we have RDI being this base, right? 4188, 4188. We want to set up our counter variable. So in this case, we're returning in RAX, so let's just make RAX be our counter variable. So we set RAX to be 0, and this is going to be how many numbers we go through. So we want to compare, or let's actually get ready to dereference. So we're going to look at RDI. We're going to compare RDI with 0, right? So RDI is the base of this list of numbers. We're comparing RDI with 0. And if it is 0, then we want to jump to done, basically, because we're done. As soon as RDI, which we'll see why we can use RDI in a second, but as soon as, let's just imagine the first case. If the very first number was in fact 0, we could jump to done and call it done. So at done, we would be done. There's nothing really to do because RAX already contains 0. We would be done if our test case just started with the first byte in our list being a null byte. But what if it's not the case that RDI is 0? Well, then this is where we're going to be executing, right here. All right. Oops. Right here is where we're executing. So what we want to do is we want to add RAX1 because we've said, hey, this byte was not 0. So we want to say that we found at least one that wasn't 0. And then another thing we can do, and there's a lot of ways to do this, but we can just add RDI1. We can say, okay, let's just now pretend the base of our list is at the next one. We don't care about keeping the original value around. Let's just add 1 to RDI. And now if we jump to, let's call it loop, oops, we are going to repeat, right? So we've added 1 to RAX, so we've counted the first one. We've added 1 to RDI. We've kind of reset where the base of our list is. And now we're comparing again RDI with 0. So now we're looking at that second element. And if it is 0, we're jumping to done, etc. So we're just going to keep looping and looping and looping until we find that null byte and we get to go to this done region. Now we're not completely done because it told us we need to pass a different constraint, which is what happens if RDI is 0. That we want to do something special for. But let's start with this. Okay. So actually, let's do an int 3 at the end as well. Was RDI 0? No, it wasn't. Okay. Okay, so for this first one, and then let's see here. What did we mess up? So it looks like we're jumping to done and RAX is still 0, despite this not containing that. Okay, so we move RAX 0. We compare RDI. Oh, here's the issue. We don't want to compare RDI with 0. We want to dereference RDI and compare that with 0. So right here, we're just comparing the address with 0, which is something we need to do, but that's not what we're trying to take care of in this case. We're trying to dereference. So in this case, instead, let's do move RBX. Let's just grab another register and dereference RDI, because that's what we're trying to compare with 0. And then also, in doing this, let's move just a single byte. So let's actually do move RBX 0. Let's zero out RBX so that there's nothing there. And then let's just move only into BL, that 1 byte, because we're just trying to grab 1 byte from memory. So let's be very explicit about that. Let's grab that single byte from memory and move that into BL. And then let's compare BL with 0. So now instead of just comparing the address with 0, we're comparing dereference the address with 0, because that's what we're really trying to do. Okay, let's see what this does for us now. Okay, so still looks like it's not happy. In this case, we went RAX to 0. Sorry, no flag. Let's see here. In this case, it grabbed RBX, said that was 50. Do we have our condition inverted? Oh, we're just jumping to done. Okay, this is the issue. We messed up the logic here. We need to do a conditional jump. We are just always instinctively, immediately jumping to done. This is not what we want to do. We only want to jump to done if they're equal, right? We don't want just this absolute jump. We want a conditional jump. So only if they're equal, if BL is equal to 0, do we jump to done. Okay, hopefully this gets us through most of the test cases. We're still missing one thing, but that was an issue. Okay, we're getting tons of data. Eventually, and this is what I believe was mentioned, we get this error, invalid memory read. So let's see what our int3 instruction was telling us about when we get this invalid memory read. So we see RDI right here is set to 0, whereas in previous cases, RDI was off in this starts with 404 location. But in this case, RDI is 0. So what happens here when we do this? Ultimately, in our very first iteration, if RDI is set to 0, we're going to end up dereferencing RDI. But RDI is 0. It's location 0 in memory. It's a null pointer. So we just dereferenced a null pointer right here. And this is an issue. This is why it's telling us invalid memory read. It says that page is unmapped. And it is unmapped because the very first page in memory is always unmapped, almost always unmapped. And it's going to cause a segmentation fault. It's going to crash your program. It's going to do whatever. In the case of this challenge, it is nice to us. It doesn't just crash the program. It tells us invalid memory read. It's smart enough to actually detect that you're about to dereference a null pointer because of the way that it's implemented. But if this was a normal program, it would tell us segmentation fault. You just crashed because you dereferenced a null pointer. So what we want to do is we need to check right away, just straight at the beginning. Let's compare RDI with 0. And actually, we'll initialize RAX to 0 because it tells us specifically what it wants the result to be. Well, it told us above. We'd have to check, but it's way above in the history. It would tell us that we want RAX to be 0 if RDI is 0. So if we're being passed a null pointer, just return 0, basically. So in this case, we want to compare RDI with 0. We want to do that after we initialize RAX. Compare RDI with 0. And if RDI is 0, so if it is equal, jump equal, just jump to done. So we're just going to entirely bypass this loop if RDI is a null pointer. So this is how we would do. We think back to C. If we ever have statements that are if that value that was passed to us is null, I want you to early exit my function. This is the equivalent of that in assembly. Let's see here. We might want to get rid of the int3s because it's spamming us with tons of data, but ultimately it gives us the flag because we have now correctly done our error handling. Okay, are there any more questions on this level about this concept of dereferencing a null pointer or doing this conditional while loop? Would anyone want to see it in C, for example, what exactly we just wrote? No. Okay, awesome. Let's see here. Are there any more questions? I see people asking about 22, for example. Are there any more questions on before level 20? We'll do at least one before level 20 and then jump. Yeah. 15. Did we already look at 15? Let me quickly see what 15 looks like to make sure if we've already looked at 15 in the past. Level 15. Yeah, swapping mouse. So this is, if you go back 2 Q&As, I think you'll see level 15 in there, which are all on Twitch. So if you go to twitch.tv/pwn.college, you can see our past videos. To whatever, I guess, a week ago was from today, I would have talked about level 15, I believe. Yep. 17. Did I talk about level 17? Let's see if I recognize it is something I talked about.
Yeah.
Did I already talk about level 17? Okay. Does anyone know which Q&A was 17? Last, so 2 ago? Okay, so if you go back a week and you'll see I talked about level 17, hopefully answers your questions. If it does not, definitely feel free to ask on the Discord if you need more clarification about 17. But that, okay, so let's just jump to 22 because there's tons of people spamming about level 22. There's lots of interest in 22. Okay. Okay, so it looks like we're given this quasi-C, quasi-assembly, quasi-Python logic that we want to implement. Okay, but let's see what we're talking about. I saw the word function. Are we talking about functions here? All of which will be contained in a function. Function is a callable segment of code, does not destroy control flow. Let's see here. We use call and ret within x86 to make that happen. The call instruction pushes the memory address of the next instruction onto the stack and then jumps to the value stored in the first argument. Okay, so for example, we might have some function located at 4,000, 4 million, whatever this is. And then we call RAX, so we jump there. And then after the code here, that this logic contained at this location in memory has a bunch of instructions. Eventually, it's going to terminate in a ret instruction, which is going to continue control flow to here now. So basically, we can kind of imagine like, in some sense, we're embedding potentially thousands of instructions just into this call, and then we get to return back and continue on. Okay. Whereas a jump right doesn't necessarily come back to us unless we have another jump that specifically returns back to us. But a call is very encapsulated. As we've probably seen in all sorts of programming languages, the concept of calling a function. It comes back to us after it's done with the function. Okay, so call pushes, in this case, and this is how it's implemented, and actually we'll look at it in a second. The first thing that call does is it uses the stack. It pushes 102A to the stack. And what is 102A? It's the address of the next instruction for when we return. So it just immediately saves this. And the reason that it pushes this to the stack rather than stores it in a register is, what if we have lots of deep nested function calls? We might run out of registers to store addresses to return to into, right? We might have a recursive function that calls itself thousands of times. We don't have thousands of registers. So ultimately, in order to be safe, we need to save where we're returning to in memory, because we do have thousands of places in memory to store addresses. We don't have thousands of registers. So we save the location we're going to return to eventually on the stack. And then we basically do a jump. So basically all a call is that it is a push RIP and then a jump argument. So it's just a push followed by a jump. That's all a call is. And then a ret is just effectively a ret is just a pop RIP eventually. So it's just going to pop off the stack, and that's going to set RIP to that value. So it might sound a little crazy to be like directly manipulating RIP without using control flow instructions like calls and jumps and stuff. But you can imagine the concept of a pop RIP, just popping straight off the stack into the instruction pointer, and now we're resuming there. That's all a ret instruction is. It's just pop RIP. Okay. So let's see here what it's talking about. Move, RAX, RDX, ret. So this is a very simple function. All this function does is it moves RDX into RAX and then it rets. And then where would we ret to? We would ret to 102A because we would have pushed. So nothing here is using the stack, so we don't even have to think about the stack. we would have pushed 102A to the stack, and then we would pop that into RIP. And so now we would jump back to 102A. And maybe we'll look at that quickly in GDB just to make sure it's honed in, because this is a super important concept of how functions are implemented at an x86 level. Please implement the following logic. So stir lower, I'm guessing what we're about to do is lowercase a string, potentially. Let's see, RAX is 0. If source adder, so we're doing a null check here basically. So if we're not being passed a null address, then what we're going to do is we're going to walk along this region of memory. In the same way that in the last level we just kind of walked through memory 1 byte at a time, we're about to walk through memory 1 byte at a time until we reach the end of our string. And the end of our string is just a null byte. And then, so if source adder is less than hex 90, we are going to say that that location memory, that single character, that single byte, needs to be replaced with the result of calling foo. So presumably foo is kind of like this lowercase my character function. We pass that in here, RAX plus equals 1, source adder plus equals 1. So let's see. Oh, we lost our SSH. Did we lose Twitch? No, we did not. Okay. Let's see what this logic might look like within Python real quick. Just because it's probably a little bit easier to think in Python or C or a higher level language, and then we'll implement that, or at least implement part of it in x86. So if we wanted to define some function called stir lower, which takes some list, what we would be doing here is, and I guess REX equals 0. Oh, that's just our counter. Okay. So we would say, we'll even call it REX. REX equals 0. And we want to check if, will be Python-ish. If list is not an empty list, let's just say, because that's kind of the equivalent, but you know what, we'll just say it's not 0, who cares? If list does not equal 0, then what we're going to do is while list of, actually, how do we want to show this? Getting into Python, this makes this actually a little bit more confusing. Here's what we'll do. We will, instead of using Python lists, we will use a byte string, which will make sense in a second. Or actually, we'll just use a string. Let's say that stir or s equals a, b, c, d, e, f, null bytes. We just have this string here. We're creating this function stir lower. It's going to take in some string. Here, we can call this string. We'll say RAX equals 0. We'll say if the string does not equal 0. This doesn't really make sense in Python, but we'll just keep following the logic. And then we would say while, actually, we'll even follow the naming convention as well. Source adder. So we would say while source adder sub RAX. Actually, no, we don't even need to do that. No, implementing this in Python might actually make things more confusing because we're just going to be doing too many Python-y things rather than this logic. Let's just jump straight into assembly. Okay. Let's start with our int3 instruction. And 22. Okay, so this is the initial state of our code. So we're given data at 40400, which is a bunch of random bytes. Oh, that's an example run. RDI contains where it's going to be. So in this case, RDI contains this value, which is right here. So again, just like the previous level, we just have a bunch of random bytes. Initially, I guess we're told invalid memory read, which is interesting, but we'll deal with that later. Let's see here. So we want to do the following. Foo is provided at this location. So if we want to call foo, we need to call to this address. It takes a single argument as a value, And that single argument, by calling convention, is going to go into RDI. We pass the first argument of a function in RDI. This is just a standard. There's no specific reason to do this, except that everyone has agreed that functions will take the first argument in RDI. That is why RDI is used. So we're going to take a single argument, and then we need to do this. Okay, so we are just straight implementing this function. Presumably there's like scaffolding around this that's going to call into us. So the first thing we should probably do is check to see if source adder, which in our case, right, because we're implementing a function, is going to be in RDI, if that is 0. So in this first case, we can see it's not 0, but let's just start by following that first thing that we need to implement. So let's compare. Do we want to do that, or do we just assume it's not 0 and deal with that later? We'll deal with it later. Let's ignore this statement. We don't even care. We'll deal with that at the end. We're going to follow the same logic as before. Actually, let's just jump to our previous logic that we had before, because we already have something that's going to walk through a list of numbers or walk through memory comparing for zeros, right? In this case, we have this counter, right? If we think back to level 21, we have this counter that's being incremented every time it is not 0. And as soon as it is 0, we jump out to being done. And in this case, right, the difference here is now we're not just implementing a bit of logic, we're implementing a function. And the difference with implementing a function versus just a little segment of logic, if we want to be encapsulated, we need to call ret at the end. So we're calling ret. And fortunately for us, the previous level already had us using RDI, which is the equivalent to the first argument. So that's very nice. So we've got our first argument being compared to 0, and we're done if it is, right? If we're past the null pointer, we're just done. We're going to just straight ret. Otherwise, we're going to jump into this loop, and we're comparing within our loop, we're comparing that single byte. We're walking along memory. We're dereferencing. We're comparing the byte, see if it's a 0. If it is a 0, we jump out to done because we're done. Otherwise, if it's not 0, we're not done with our string yet. This is where we do our logic. So our logic all happens right in here. This is the interesting bit of the code in some sense. If we ignore all of this surrounding control flow, this is the inner part of our loop. And in this case, we're just adding 1 to RAX. We're incrementing our counter. And we are adding 1 to RDI to go to the next byte in memory. Okay, so this is kind of this while loop implemented. And now the question is, what do we do on the inside? Again, source adder is being added 1 to it. This is how they implement it. There's probably multiple ways to do that. In that same way, we are adding 1 to RDI. That's how we're incrementing our source adder. So what we want to do is on the inside of this loop, we want to do a condition. And we only want to add 1 to RAX. So right now, we're always adding 1 to RAX. We no longer want to do that. We only sometimes want to add 1 to RAX. And when do we want to add 1 to RAX? Only if that byte that we dereferenced, so the dereferenced value, it's a single byte, it's currently sitting in BL, right? That's what we're comparing with 0. BL contains that single byte that we're focused on right now at this iteration of the loop. We want to compare that with 90. Is it 90 or hex 90? I guess it just says 90. So we will compare that with 90. So right in here, we want to compare BL, which contains that single byte memory we're looking at, compare that with 90. And if it's not equal, we'll just create another label. See how we're doing this in a second. Not 90, right? We'll just call it not 90 as our label. If it's not equal or less than, yeah, true, good call. So if it's greater than 90, we want to just invert this. If it's greater than 90, that's when we don't want to execute this logic. So if it's greater than 90, right, we're just kind of inverting the condition. If it's greater than 90, we don't want to add 1 to RAX because it only says if it's less than or equal that we want to do that. We'll just call this greater than. Jump greater to greater, right? We're jumping to that region. We're not doing this add 1 to RAX. We're just jumping to greater instead. We're skipping that. We're not adding 1 to RAX. Only add 1 to RAX if it's less than or equal to. Hopefully that makes sense. Very explicit. But we're missing one thing. We're missing this statement. This is the only statement we're missing right now within this whole code is doing this operation now. So again, we've already dereferenced source adder. That's sitting in BL. We want to move that into RDI and call foo. So ultimately, we're going to call this address right here. So we added 1 to RAX. Let's see here, right? RAX is 1. We do that at the end or whatever. And oops, nope. We want to get ready to jump to this address right here. So we want to call this address. We can't exactly do it that way. We need to put this address, I believe, well, maybe we can, I'm not sure, but we'll be safe. We'll move this address into a register and then call that register. So let's just randomly use R10, random register. Let's move R10 to this address right here, and then we'll call R10. Okay, so the only thing we're missing now, so this is our comparison statement. This is if we are in fact less than or equal to 90, this is all of this logic. We're going to execute this if it's less than or equal to 90. So we think of our indentation, we think of our scoping. This is inside that if it's less than or equal to 90. We need to pass our parameter. And how do we pass the parameter? We move it into RDI. What are we moving into RDI? We're moving that single byte. And that single byte is currently sitting in BL. So this is kind of something going on here as we're typing up all this assembly ourselves, as we're keeping track of all of these registers. All of these registers have semantic meanings in our mind. And we need to just kind of keep a running list in our head of what RAX is, what BL is, what RDI is, what all these things are, and what they are at any given point in time, right? Because we're playing this game of shuffling registers around and manipulating registers and stuff. We've only got a small number of, kind of in the C world, variables that we have access to. And we need to just shuffle them around and be very careful about them and remember what they all mean. So BL, as we remember, is when we dereferenced RDI. We put that into BL. So that is our single byte. And where does that need to go? That needs to go into RDI so that we can do our call. Okay. Yes, there's exactly. So yeah, you just pointed out a massive problem here. And this is what I'm talking about, that we're playing this register shuffling game, is we have a problem. So if we want to call this function, the calling convention says that we need to put our first argument into RDI. Well, guess what? We're using RDI. RDI is the super important value. That's our function's value that we're manipulating, right? You can see here, we're like adding 1 to RDI. We're like comparing, we're dereferencing RDI. We're doing all of these things, right? RDI is super important to us. But we just moved into RDI BL. We just clobbered it. So we no longer would have our value. So this is kind of a nightmare, because what this means for us now is either we need to move our registers around, kind of refactor all of our registers, or we need to somehow just save this value. You could take either approach. Hopefully, does everyone understand what I'm talking about here? Is anyone confused, right? What this is introducing to our program. This is a problem. We're clobbering RDI, we're losing that value. We need to know RDI, but we just overrode it with some other value. We need to persist RDI somehow so we can get it back. And when do we want to get it back? Well, after this call, we kind of want to just get RDI back. So what we can do, we'll just use the stack for now. This is the simplest option probably in my mind. You could also move RDI into a different register, but let's just push RDI onto the stack and then pop RDI off of the stack right here. This is kind of what the stack is meant for, it's just like scratch space. So we push RDI onto the stack. So now we've kind of saved the value of RDI into memory on the stack. And then when we want to restore it, we just pop RDI. So we've saved it to the stack, and then we've restored it from the stack. So inside of this region, in between this push and this pop, it's fine if we clobber RDI because we've persisted it somewhere else. Okay, so that is one thing. We have one other issue though, and that again goes back to the calling convention. So the calling convention says that the first argument goes into RDI. Why RDI? Because everyone agreed that RDI is where the first argument goes. There's no better reason than because everyone says RDI is the first argument. So all these libraries and function calls can all interoperate, and everyone knows go to RDI for your first argument. Well, the calling convention also says that the result of a function goes into RAX. So we can see up here, when we do this equal, right, we're taking the result of this function call and putting it here. Well, the result goes into RAX. So by calling R10, we just lost RAX. And RAX is also an important value to us because we're adding one. Eventually, we're going to return RAX because RAX says the calling convention is our return value. Eventually, when we ret, effectively, the person calling us is going to look at RAX. We need to also save RAX. So let's go ahead and so we push RDI. And then after, let's push RAX, and we need to go in reverse order. So we can kind of think of it as inside of here, RDI is fine. We've saved RDI. It's good to go. If someone clobbers it, we're totally safe. Well, now inside of here, RAX is safe because we've also saved RAX. So we're almost there. The only thing we're missing now, potentially, maybe we're missing lots of things, but the only thing that's standing out to me right now that we're missing is that we need to use the result. So we need to use RAX to write to memory because we take the result of this, we throw this into memory at this location. So you might think we would do like move BL RAX or something, which is certainly an option. And actually, just to be safe, because I'm not entirely sure what the assembler is going to tell us with things like this, where it's like moving 1 byte into 8 bytes, let's just go ahead and be safe. Let's say move RDI 0 and move DIL BL, right? So that way we're just working on 8 bytes and then we're working on a single byte. We'll do that to be safe because I don't actually know what the assembler is going to tell us. The same way here, we've got this result sitting in AL. Really, it's sitting in RAX, but the only part we care about is AL because we only care about that single byte. We need to move this into memory. So what you might think is we would just do like move DL AL, right? Because we're, oops, not DL, BL. Because we just said before, right, if we think about everything semantically, BL is containing that single byte we were looking at, right? BL contains bracket, source adder, bracket. That is what BL means in our mind right now. But the issue is when we want to persist this, when we want to like actually take the result and store it somewhere, BL isn't memory. BL is just a register. So even though we're using BL from when we read from this location here, we need to actually save it back. So we need to put this back in memory. So we can temporarily say move BL AL, but the thing we need to do is we need to actually write that back to memory. So what does that mean? We need to do, well, hold on. So we've saved BL, right? We've said, okay, BL now contains the new value here. After we restore RDI, because RDI contains where we're actually at in memory, so for completeness sake, we could imagine doing it here. We could say move RDI BL, right? We want to write it back out to memory because in the same way that we pulled from memory to make BL become a thing that we care about, we could write BL back into memory at bracket RDI. But the thing is, RDI is currently this value here. Move RDI 0. Okay, well, we need to fix that. But either way, RDI is when we set up for this call, right? When we did this call, we've said the first argument goes in RDI. We haven't restored it yet from when we did this push, so we need to do it after this push, and so after the pop. So when we restore RDI, we need to write back to memory right here. So after we have restored RDI to its former glory, we get to write back to memory. Okay, one other thing that now I'm noticing is move RDI 0. We didn't want to move RDI 0. We wanted to move RDI. Oh, no, we did, because this is a two-step thing. That's what we were doing. Right. This is kind of two instructions to do the one thing of moving BL into RDI. Right. Okay, so we're good there. Okay, so we restore RDI to its former glory, what its value was before we did all this call setup stuff, and we write back to memory. So hopefully you can see that there's like kind of some structure to all of this, right? We have this concept of persisting values using the stack. So like inside of this push pop like segment, we kind of have like this scope thing where we're saved RDI and then we restore RDI. So inside of this region, we can do whatever we want to RDI. Same way we create one of those regions with RAX. So now we can do whatever we want to RAX and then it gets restored on the way out. in order to call, right? We're clobbering RDI to set that first register, to pass that first argument, et cetera, et cetera, et cetera. Okay, so there's kind of a lot of logic here. You have to keep a lot of things in your mind. This is one of the many reasons that something like C exists, right? Because we're playing all of these register games, we're playing all of these memory games, persisting things, et cetera. This is kind of the whole point of C, is that C is going to play this game for you. You're going to write higher order concepts, and the compiler is just going to play this register persistence game for you, and you don't have to think about it. But this program is not too complicated. We can reason about this all in our head and do it ourselves, which is what we're doing here. It's good exercise to make sure you understand really what your computer is doing. But that is, of course, why we have C. Okay, let's see. Of course, we did not ever run this. Let's see what happens. We have a lot of int3s. Probably going to need to delete those int3s. But in the end, we one-shot this program. We managed to write it once and execute once. We started from the base of the previous level. They kind of gave us that whole... Okay, we're going to have to... Let's go back to... Hold on. Challenge. Embryo, that. We started on the previous level, which was very similar to this level. It's just the only difference was that we had this embedded into that while loop, right? This level is the exact same thing as the previous level, except we need to add this into our while loop. And we also wanted to make this a function, right? Otherwise, it's the same thing. So we started with that as a base, and then we figured out how to do this, right? This is nothing more than a compare. We just do a compare, and then the real tricky thing is this right here, which requires us to be very careful with our registers, persist registers, because we're going to be clobbering them to make the function call, so we want to push them onto the stack, and then we want to restore them. This statement here is a little tricky for sure, but hopefully it makes sense why we had to do all of the things that we did in order to make the function call happen. The reason we had to do all those things because of the calling convention. So everyone agrees that RDI is the first argument. You could imagine a chaotic world where everyone's passing arguments in different ways, and you don't have to do all this persistent stuff because you know throughout your entire program where everything wants to be stored. But because of the calling convention, we've got to be ready to destroy RDI in order to make this function call happen. And that's really sad for us because we had our own RDI. So we need to persist it so that we can modify it. Okay, any questions on this level? Or any of the concepts in this level? It's definitely a little tricky. It takes a little bit of time walking through the logic, probably stepping through the code yourself, understanding every single step of the way what exactly is happening. But it's super crucial to understand this because this is what your compiler is doing when you're writing C. It's just generating stuff like that to make it all happen. Okay, no questions on this. Well, we're unfortunately at the end of time for this class. So if there's more questions, continue to ask on Discord. And thank you all for attending today. See ya.